Okay, so our second speaker today is WillieRushLim from Stony Brook University, and he will tell us about Herman rings and Herman curves. So please.
Thank you for the introduction. Thank you for having me here. So today I'm going to talk about Herman rings and Herman curves. I would assume that some people here are familiar with the definition of Herman rings, but we're also going to talk about this new object that I'm going to call Herman curves. That will be more towards the second half of the talk. Okay. So what's the context? I'm going to talk about complex dynamics, which means that I will be interested in the study of holomorphic submaps of complex manifolds. And this is the study of dynamics, which means that I take iterate of the points on the phase space and study the orbit to see what happens, whether it converges to, say, a periodic cycle, or whether it accumulates on some funny continuum or whatsoever, right? And then the context of today is also we also have this dichotomy. So just a reminder for everyone that we have the Fatou set and we have the Juliet set, where the Fatou set is set of regular points. The formalism here is in terms of normality, and Juliet set is the set of chaotic points, which is the complement. But for today, we're just going to stick with the the space of rational maps on the Riemann sphere. So M, we're going to take this to be the Riemann sphere, and automatically the space of holomorphic maps on M would be the space of rational maps. And for non-triviality reasons, we got to take the degree to be at least 2. And I want to focus on a particular dynamical behavior for rational maps, which is rotational dynamics. So I call a domain on the Riemann sphere a rotation domain if the F is conjugate to rigid rotation on U. And there are 2 types of rotation domains. It depends on the topology. If it's interconnected, we call this a single disk. This is just a topological disk that is rotated around by F. And then if it's not a disk, then it must be an annulus, and we call this a Herman ring. Okay. So here are 2 examples of each of these 2. The one on the left here is realized by F equals to Z plus C. So this is the quadratic family. And then inside the quadratic family here, I have a fixed point that I can make this to be an eigenvalue, which is of modulus 1. And in fact, this is just an algebraic computation. And then if I make this, the argument to be of, say, the golden mean, this is actually the corresponding single disk I have. So historically, single disks are they're realized by the study of analytic linearization of neutral fixed points. And the one on the right here is an example of a Herman ring. You can probably notice that the formula that I have here, this is a Blaschke product, a cubic Blaschke product. And then this expression alone without the e to the whatever over here, actually this is tells me that I actually have an invariant unit circle. And in fact, this is a homeomorphism. And also there is only a single critical point on the unit circle. This is a critical circle map. And then I can twist it a bit by multiplying it by this, complex number of modulus 1. And then I pick some corresponding parameters so that the corresponding critical circle map has a golden mean rotation number. And it produces me not just one single invariant curve, but in fact a foliation of such inside this Herman ring. Okay. And historically, Herman rings were produced, the first 2 examples were realized as, what do you get out of analytic linearizability of circle diffeomorphism? Oh, sorry, I think I mentioned earlier that there's a single critical point. That's not true. There should be 2 of them over here. They're different. It's a critical circle map. It's a circle diffeomorphism. So what I want to focus on today as well is I want to emphasize on a certain assumption, which I call the Bowler-Cup assumption. So if you look at the corresponding rotation number, this is it must be an irrational number. I'm going to assume that it's a Bowler-Cup. So what this means is that when I look at the continuous fraction expansion, okay, I look at the terms, and then this must be uniformly bounded by some constant. And then throughout this talk, I'm going to denote the dig B as the bound on the rotation number, on the continuous fraction expansion. Okay. And for example, just to remind you guys, we have this golden example, the golden mean. This is where the terms is just all one. Okay. And basically, the Bowler-Cup assumption will tell us something about the regularity of our rotation domain. So there's a general theorem by Kahn about 12 years ago that states that if I have an invariant equal disk of a rational map, this must be a quasi-disk. Okay. And not only that, it also contains a critical point on the boundary. And another thing I have to emphasize from this theorem is that the regularity of the single disk, the dilatation of the single disk, okay, as a quasi-disk, it depends only on the degree of the rational map and the bound on the rotation number. Okay. I want to say as well that the for subclass class C, for the quadratic family, this observation follows from Duadi and Jish using relying on a result by Herman and Swatek. And then this was later generalized by Lyubich for cubic polynomials. And then generalization for all polynomials was done by Shishikura, and then Shishikura's method was later generalized by Kahn himself. Okay. And what I want to move on to is, I'm going to go on to the Herman rings as well. So there's a general procedure in fabricating Herman rings, and this is called a Shishikura surgery. So what you can do is you can start with single disk, and there's a way to convert single disk into Herman rings. And actually, there's also the converse, which is to convert Herman rings into single disk. And all of this is done via quasiconformal surgery. So to give you a brief summary as to how it works is that suppose you start with a pair of single disks, so a pair of rational maps, say F1, F2. And then what you want is you assume that the rotation number is complementary. So one is beta, the other one is 1 minus beta. And you pick invariant curve inside, you pick another invariant curve inside, and what you want to do is you want to delete the disk inside of it. Okay? You delete, you only care about the dynamics outside of the invariant curve. You only care about the one outside of the invariant curve, and what you do is you basically glue along this invariant curve together. So these two dynamical systems are glued together. And this gluing procedure, what it produces me is basically, so after, I guess, a bunch of interpolation and QC conformal correction, you actually get a Herman ring where outside of this curve here, this dynamical system, or outside of this, invariant curve, actually mimics, or in other words, is QC conjugate to the original F1 over here, and then part that's inside is QC conjugate to the dynamics outside.
So quick
F2.
question, Willie,
Yes.
you do need the same rotation numbers to be able to do this?
So this is theta and 1 minus theta.
Oh, theta and 1.
And then in the end, you get a rotation number theta.
Okay, got it.
Yeah. And then just a quick reminder is not what I said, which is I can convert a Herman ring into single disk. This one is more straightforward. What you do is you pick another invariant curve, and then you basically ignore everything inside and basically paste just a rotational disk. So what you get is now this, Herman ring becomes a single disk. Okay. So some results earlier on the fact that single disks with bounded type rotation number are quasi disks. I also have a similar result for Herman rings. So by this surgery procedure, I can transfer fairly easily. And now I have this statement that if I have a rational map, and this rational map has an invariant Herman ring or bounded type rotation number, now it's again, the boundary components are again quasicircles containing a critical point. But there's a twist in this, which is, the procedure that we do, it gives me an additional parameter in the dilatation. So earlier, I noticed that the dilatation as a quasicircle, it depends on two parameters, which is the degree and the boundary rotation number. But in the QC surgery, we also have an extra parameter that comes into play, which is the modulus, the conformal modulus of the Herman ring. And in general, this dilatation can be really bad when the modulus is very small, okay, just by this observation. But I'm going to argue that this is not quite the case. I'm going to delete this dependence on the modulus in the next slide. So now I'm going to talk about a particular class of Herman rings with the following assumptions. I will fix two integers, d0, d infinity. And I'm going to look at the space h, curly h here, of degree d0 plus d infinity minus 1 rational maps with the following properties. So there's a few assumptions here, but I'm going to try to draw what's going on. So if I say take d0 to be 3 and then d infinity to be 4, I'm going to assume that f has critical fixed points at 0 and infinity of the corresponding digits. So 0 is 6, say 3, 2, 1, and then infinity is also fixed, say 4, 2, 1. And then second assumption is I have a Herman ring of rotation number theta. And again, I'm going to assume that theta is of bounded type. And then 3 tells me that it must separate 0 and infinity. So this is the rough picture. And then 4 is a minimality assumption that all the other critical points lie on the boundary. So because 0 is 3, 2, 1, then I will have 2 pre-images of a Herman ring like that. And each of them is attached to the Herman ring. And then on the outside as well, I also have outer pre-images. You can have multiple if it has a multiple criticality. Something like this. Okay. And the statements that I'm going to make is with regards to the dilatation of the Herman ring. So following from the previous statements. And this is what I call a priori maps, which is whenever I have a rational map in this class, so the dynamical picture is the one that I drew earlier. The boundary components are again quasicircles, but now I can say for sure that the dilatation is independent of the modulus. It only depends on the pair of integers, the degree I have, as well as the bound on the rotation number.
Do you actually get examples where the modulus is arbitrarily small?
Yeah. Yeah. Yeah, at this point, anyone have any questions? Okay, so what I want to do is I'm going to try to give a brief capture the ideas behind it, and then move on to the consequences. So how do we do this? We start by selecting one of the two boundary components. That's an annulus, that's an outer one, that's an inner one. So let's say I'm going to select the outer one and call it H. Big H, capital H. And then I'm going to endow H with the combinatorial metric. This is the unique normalized F invariant metric. It's a unique one because I know that, this is just, irrational rotation around, and it comes with a unique normalized ergodic measure. And I'm going to select an interval in H of some small combinatorial length, say, less than 0.1. Suppose maybe it's 0.01. Right? And then if I select such an interval, I'm going to denote by 10i the interval where the length is now 10 times the original. And the midpoint is still the same. So if say I have this is I, then 10i would look something like, I don't know, way longer. But it has the same combinatorial midpoint. But what I'm going to do is I'm going to play with the extremal width of curves connecting I and the complement of 10 times. Okay, so just a reminder that extremal width here is the reciprocal of the extremal length. So if you're familiar with extremal length, well, the extremal width is just the reciprocal. So I have to pick, look at the set of curves connecting the I, and you delete 10i, you get H minus 10i. And you can also think of this as the reciprocal of the modulus of the complement. So this is the modulus of this annulus. Okay. And in general, when this quantity is very small, then the quantity and the H in general is it could be very regular. But if this W10 width is large, then that means that this is a picture in the sense that there will be some part of this H minus 10i that will be very, very, very close, and you get a large width of curves are connected to the I and H minus 10i. So in some sense, this quantity encodes the local near degeneration of H near the interval. Okay, and this quantity, whenever it's very large, this is really the bad situation that we're in, and this is the source of very high dilatation as a quasicircle. So what we want to do is we want to find a uniform bound. So if I select any interval I on the boundary on H of sufficiently small length, I want to make sure that it's uniformly bounded. The W10 width is uniformly bounded by some constants. And then I want to make sure that all these constants are independent on the modulus. They only depend on the degrees and the bounds on the continued fraction expression. And how it is done is we go by contradiction. So if we assume that there is a sufficiently small interval with sufficiently large width, then I want to prove that somehow along the lines I can find another interval again of sufficiently small length, so sufficiently deep on the quasicircle, but then the width is now amplified at least 2 times. Okay. So this is what's called the philosophy is called the near-degenerate regime. And when life is already very bad, now it's going to be even worse tomorrow. Oh, and within this game, I also want to make sure that all the bounds here depend only on the degrees and the bound on the b on the rotation number. So just a quick note on the proof. I'm not going to go into details, but the main ingredients here is the analysis of near-degenerate surfaces that was initially introduced by Lyubich and Jeremy Kahn, and there's also recent work by Dudko and Lyubich. So quasi-additivity law and the covering lemma, this was introduced in the game by Jeremy Kahn and Lyubich. And then the original motivation behind this is to prove the a priori bound for infinitely renormalizable quadratic polynomials of bounded primitive combinatorics. This is done by Jeremy Kahn. And within his proof as well, he also used the language of canonical arc diagrams. This is basically a way of encoding degeneration of surfaces as arcs, as weighted arcs. And then this idea was also used recently by Dudko and Lyubich. And this, the motivation is different. This is on the study of uniform a priori bounds on neutral fixed points on single disks. Okay. This is where the terminology W10I is also introduced. But I do want to emphasize that the proof that we have here was not is probably closer to Jeremy Kahn's argument. But there's some similarities with the quadratic light case in Jeremy Kahn and Lyubich. But it's also some similarities on the Siegel case. But they are, you know, in the technical level, they're quite different. So I don't want to bombard you with the details. I'm going to try to move on to the consequences on a priori bounds. And I will introduce a new object. So instead of talking about rotation domains, I can talk about rotation curves instead. So the idea is similar. I have an invariant object, invariant curve, that on which the map is conjugate to irrational rotation. So we have a Jordan curve, and then f just acts as an irrational rotation. And we can get rotation curves out of invariant curves of rotation domains. That is something that we know already. On the boundary as well, if the boundary is regular, if the boundary is Jordan curve or a quasicircle, the dynamics is also gonna be rotational. But we can also have rotation curves that are not inside the closure of rotation domain. And here I'm gonna call it a Herman. Okay. So there are three cases. And when I have a rotation curve, there are three possibilities. One is either it is an analytic curve inside the rotation domain. So let me try to draw three different possibilities. So the first one here, basically, this sits inside the foliage on the rotation domain, either the Herman ring or Siegel disk. The second possibility is if it lies on the boundary of a rotation domain. And so it also comes with a foliation, but only on one side. And then on the other side, it will have a critical point. So if I take a preimage, then you get something like this. And now the third possibility is this is the Herman curve. And this can only occur under the bounded type assumption. It can only occur when you have an inner critical point and also an outer critical point. Okay. So this one, well, it doesn't come with a foliation at all. But what's stopping it from having a foliation of invariant curves is, you know, the critical points. Really. So let's look at some examples. This one is a trivial example, meaning that the Herman curve is just a unit circle. So if I pick any irrational number, it doesn't have to be of valid type, actually. I can actually find a complex number of modulus 1, so lying on the unit circle, such that the following rational map, this degree 3 rational map, this is actually a Blasky product. So it leaves the unit circle invariant. And actually here, I defined it so that the unit circle is a Herman curve of the correct rotation number theta that I choose. And the picture of the Julia set is the following. And you can easily identify where the unit circle is. This is invariant. And in fact, this is a critical circle map. It has a unique critical point. And then if I take the pre-images of the unit circle, this would be this guy and this guy. There's one inside and there's one outside. Okay. But the question that you can ask is, can I find non-trivial Herman curves? In other words, can I find examples of Herman curves that are not just the unit circle? Okay. So the study of invariant curves was initially dated all the way back to part 2 in 1920s. But more recently, this was formalized by Herman did this particular question a few years back. And I'm going to give them a positive answer using a priori values. And this requires me to talk about the notion of combinatorics. So if I have a Herman curve, the combinatorics will refer to the relative combinatorial position as well as the criticality of the critical points. So what does this mean? So if I have a Herman curve, suppose it has 3 critical points, 1, 2, 3. If I look at, if I take the pre-images, then it will allow me to count how many of them are there. Suppose it's something like that, which means that if I linearize this, so I know that this is conjugate to just irrational rotation on the unit circle, then I record the combinatorial position of the critical points. And then I count, okay, how many critical points I have. There's 1 on the bottom, and then there's 3 over here on the right. 3 on the right here, there's 1 inner one, and there's 2 outer ones. And then the one at the top it corresponds to 1 outer critical point. And relative here is with respect to the combinatorial metric. Okay. And so if I have a different Herman curve, but then the combinatorial data is the same under linearization, then I call this combinatorial equivalence. And so, okay, so this theorem will tell me that I can actually realize arbitrary combinatorics. In particular, I will answer the question by Herman earlier. If I choose any bounded type rotation number and any combinatorial data, I can say for sure that there exists some rational map. This page, so remember that this page here, this is the space of rational maps containing the Herman rings. And then the boundary here, it's not quite the boundary per se, but this is more like the accumulation set of curly H as well. As a space of Herman rings. And if you look at the accumulation space, then there exists a rational map that admits a Herman quasicircle. This is just a Herman curve, but then I know that the curve here is regular. It has the regularity of quasicircle, and then it also has the rotation number that I chose, and also the prescribed combinatorics that I chose as well. And the second part of this theorem is the rigidity bit, where I can also say that F is unique up to conformal conjugacy. So just to give you the idea of how it works, if I look at the family H that I start with, then I know for sure that this is going to be, a space of Herman rings. And if I look at the images, it's going to be something like that. In this case, D naught is 3, and then D infinity is equal to 4. Okay, just an example. And then if I look at the boundary of H, so I look at the accumulation space. I also have a similar picture, but now instead of a Herman ring, I have a Herman set. And then I can say draw the pre-images as well. Like that. Okay. And then the statement here is saying that, well, if I pick, say, the following combinatorics, say the one that I drew before, I can always realize it. Okay. So there exists such a map with the following diagram. And in fact, it's unique up to conformal conjugacy. So this one is, I can try to explain the idea behind. So using a priori bound, I can say for sure that I get some notion of precompact, meaning that if I select any small epsilon, and if I restrict my space of Herman rings to have of modulus bounded above by epsilon, in fact, this is precompact inside the space of rational maps. And then my space of rational maps here, I also take modulo conformal conjugacy, just to make it normalized. And the next is, how do I get to realize the correct combinatorics? So in the space of Herman rings that we have in the curly H, we have an answer for that already. This was a problem that was studied by Xiaofeng Wang about 10 years ago, 11 years ago. And this is some kind of certain type result for Herman rings, which states that if I want to have a rational map with a Herman ring, or even a Sigoldic well, but outside of this rotation domain, it's post-critically finite outside. And also it doesn't have certain obstructions. Then I can realize it. And this, in our context, it gives me the answer for the curly H, which is there exists a map, a rational map, whose Herman ring has the combinatorics similar to the chosen one. And what I mean by the chosen one, it means that, well, if I choose the, say, the following combinatorics, say 1, 1, 2, and then 1, then I can, get this rational map F1, and the space is going to look like the following. Basically, the one I drew before. Okay. And what I want to do next is I'm going to apply a deformation technique. So each of these Herman rings comes with a moduli space. It comes with a natural maximal space associated to it. And what I mean by that is that, on the Herman ring, I can basically tweak the complex structure inside a Herman ring, so that if initially the Herman ring is what it looks like, now it's going to get deformed into something even skinnier, and even skinnier. And in general, I get a normalized family of rational maps in curly H with the same combinatorics, but then now the modulus is the one that's different. The modulus now can go to 0 as say some parameter t goes to 0. Okay. And then let's see what happens as the modulus goes to 0. I know about a priori bounds that I can take limits. Okay, I can take limits. And so therefore, in particular, this family, as the modulus goes to 0, it converges to a limiting rational map with the same degree. And by compactness of quasicircles of bounded dilatation, so this uses a priori bounds I had earlier, these quasi-annuli will have to converge to a quasicircle, and the rotational dynamics will survive. So this is a Herman curve, a Herman quasicircle. And by design, all these things have the same combinatorics, and therefore the combinatorics that I chose are now inherited. And that will be the answer to the first part, the realization part of the theorem. Okay. And this also answers a question by Eremenko. What I can do is, in order to produce Herman curves that are not unit circles, I can just, choose any combinatorial data that I want to be non-symmetric. It doesn't have the same inner and outer degrees for every critical point. Okay. And the second part concerns the rigidity bits. And this one, I have to introduce the notion of invariant line field. So just by its name, you can imagine a field of basically lines on tangent spaces of points on the Riemann sphere. But I can I'm gonna down here. This is a more formal definition, which is I take a Gauss-Family differential on the Riemann sphere of measurable regularity, and then I want to assume that this is invariant under F almost everywhere, and is only supported on a positive area subset of the Julia set. So outside of this positive area subset, you can take the mu to be 0. But on the supports, I also assume that this is just normalized to be 1. Okay. So only the direction method. And hence, I get the name line fields. So historically, we care about invariant line fields because this is very much connected to studying the deformation space supported on the Julia set of rational maths. Okay. So when we talk about rigidity of rational maths, we care about the absence of invariant line fields. We don't want invariant line fields to exist. And so the rigidity results that I stated before, actually this follows from a more general rigidity results. And this only has the following assumption. This is what I call de-rotationality. And what it means is that, so I look at the Julia set, I record the critical points on the Julia set. And I want to see what happens under iteration. I can allow them to have finite orbits. That's fine. And if they don't have finite orbits, I want to assume that it's eventually mapped to some bounded type rotation curve. I guess for some extra, I also want to assume that it's a quasicircle as well. Under these assumptions, then I can say for sure that the Julia set does not support any invariant line fields. Okay. Of course, the map that we have earlier, it satisfies the following assumption. It's definitely de-rotational. And this is also more general in the sense that, well, if this assumption does not occur at all, if every critical point it has finite orbit, it already has a name. This is what we call we usually call this geometrically finite. Okay. So this theorem is a bit of a generalization of that. And how is this relevant to our previous rigidity result? So we start with 2 maps on the boundary of curly H that we had before, right? So we have 2 rational maps with 2 Herman quasicircles, and suppose they are combinatorially equivalent. In general, there's a procedure that allows me to promote combinatorial equivalence into QC conjugacy. This is called the pullback argument. The pullback argument basically allows me to do the following. From combinatorial equivalence, you can start by QC map that conjugates the two maps on some subset of the sphere. And then by combinatorial equivalence, I can lift this QC map into another QC map that will now be a conjugacy to a larger subset of the sphere. And again, I keep pulling back, infinitely many times, and in the limit, I get a QC map that is now a conjugacy everywhere. Okay, so that's how it works. And then by design as well, I can make sure that this is also conformal on the Fatu set. This is because on the Fatu set, the dynamics is just governed by the basis of attraction of 0 and infinity. I have the Butcher conjugacy. This can be arranged quite easily.
So
and now the question becomes,
sorry to interrupt. I have a quick question. Your theorem, do you have to assume that the Fatu set is non-empty?
No, it doesn't have to be.
But how does the pullback argument then work? I mean, if you don't have any...
Well, this is just on here.
Oh, I see.
Yeah. It's not general for all these textual maps. Because on here, on curly H, I have the assumption that 0 is fixed, infinity is fixed, and it's super attracting, and so on and so forth. So the main need here is the possibility of having positive dilatation on the Julia set. And to rule that out, we apply the fact that it supports no invariant line field. So if suppose we have positive dilatation on the Julia set, then we can normalize it and we get an invariant line field. But this will be a contradiction, and therefore, in fact, it should be of 0 dilatation almost everywhere, and by Weyer's lemma, we must have that the conjugate is in fact conformal, and therefore will be done. Okay. Okay, so let's look at some examples. So there was a work by Araceli Bonifant, Xavier Booth, and Jack Miller on the space of antipode preserving cubic rational maps. And the formula is given as such. This is characterized by the fact that it commutes with the antipodal map. The antipodal map here is -1 over Z bar, if I'm not mistaken, where basically it maps points on the sphere onto the antipodal opposites. And I also want to note that the parameter Q here, sorry, I think that's a mistake. It shouldn't be, the bar shouldn't be over here, it should be over here. Yeah, this should be a generally, this is not a holomorphic family, okay? Because it depends on Q here, but it's also a Q bar over here. This is real analytic. The parameter space picture looks like this. So this is not quite a Q parameter space, but rather the Q squared parameter space. And the reason being is FQ is actually conjugate to F negative Q. It's linearly conjugate. So to take into account the Q and minus Q, you just take the square. And then the picture that was studied by these 3 authors, this is the picture. And one of the features is the gray region over here. It's not quite the region because it's not really open, but this region is characterized by hairs. And what that means is if I select an irrational number, say of Lyubich type, there exists an analytic curve of parameters on this hair. And every point along this hair, right, it corresponds to points, say this, the one in green over here. And in a dynamical picture, I actually get a half of Herman ring of the rotation number theta that I select. And then along the hair here, as I move along and go even further, what happens is the modulus is varied, and actually it goes to 0. And by our result, in fact, this hair lands, and it lands at a point. And the landing point here will be the limit of these Herman rings, which will be a Herman curve. It will be a Herman quasicircle. Okay? And by rigidity, actually, this accumulation set is in fact just a single point. So that's one example. And another one that I have is similar to the cubic rational map that I drew earlier in the beginning, but now I can say for sure that there exists Herman curves that are non-trivial, and in fact, this is an example of an imbalanced one, where now I select D naught to be 3, and then infinity, I'm going to make it to be 2 to 1. And this is unicritical in the sense that there exists only just one critical point on the Herman quasicircle. Okay. So what happens is if I take 3 images, then we have these 2 inner bubbles inside and 1 side. I can also easily compute the corresponding formula for the rational map. And this is the one that we have, the one that I had. And what I do here is I normalize the critical points to be z equals to 1. And then the corresponding critical value, maybe I think somewhere over here, C. And then if I have the following data that 0 is mapped into itself 3 to 1, infinity is mapped into itself 3 to 1, and then 1 is mapped into C in I think the remaining criticality will be 4 to 1. If I just have the following combinatorial data, then I get the following parameter space. Okay, C, Z cubed, and this fraction over here. And then by rigidity, I know that there exists a unique parameter C, and that gives me the following picture. And this is the one I get out of, I guess, picking the rotation number to be a golden mean, because we like golden mean. Okay. And of course, I also have a similar result for, instead of 3 and 2, I get to pick these numbers to be anything. If these numbers are the same though, then I get a Blashy product, and the corresponding Herman curve will be trivial. It will be a unit circle. And out of curiosity, I got to draw the corresponding parameter space, and this is the picture. Okay, so if I look at the parameter space of this degree 4 rational maps, and I want to zoom in near the parameter C star that I had earlier, and the parameter C star lies on here. And what I do is, I sort of zoom in a bit, and I blow it up, and this is the picture that I have. And you can notice that there is, kind of similar. And there's a conjecture that states that the bifurcation locus is set similar at this special parameter, at this unique parameter contained in the Herman curve or golden mean rotation number. To answer this conjecture, well, this is still, there's some work in progress, and this work goes along the lines of proving hyperbolicity of renormalization of certain, certain renormalization operator. There's still more work that needs to be done as well. And I guess I have a minute or two. I can just briefly mention, some of the work that follows after this, which is a generalization of what we had earlier. If on the realm of rational maps, I can define dynamical object called critical quasicircle maps. So this is similar to critical circle maps, but instead of being supported on a unit circle, I allow this to be supported on a general quasicircle. And I just assume this to be to have a unique critical point. Okay. And the rigidity results that I had before, it can be generalized as follows. if I have two critical quasicircle maps of the same inner and outer criticality, so the number of inner bubbles and outer bubbles attached on the critical point is the same, and then the same Fowler type rotation number, that in fact they are quasi-conformally conjugate on the neighborhood on their invariant quasicircle. And not only that, this QC conjugacy is actually smooth. It's actually uniformly C1 plus alpha conformal on H1. Okay. As C1 plus alpha here, it means that the complex derivative exists along points on the Herman quasicircle, and then its complex derivative has alpha holder continuity regularity. Well, I think that's all the time that I have for today, and let me just stop here. Thank you very much.
Yeah, thanks a lot. Let's thank the speaker. And let me start the discussion, but maybe I stop the recording at this